Writing code is easy. Keeping code alive for years is the hard part. That is the difference between programming and software engineering. Welcome to this explainer, where we're going to unpack the critical differences between just writing some code and practicing actual software engineering at scale. If you've ever wondered why hacking together a quick app over the weekend feels so fundamentally different from maintaining a massive enterprise system, well, you are absolutely in the right place. Okay, let's dive into this cold, hard truth right out of the gate. As developers, back-end engineers, or computer science students, we so often equate our ultimate value with the immediate act of just writing code. We get laser-focused on the specific feature we're building today. But what's truly fascinating, and honestly what gets overlooked a lot, is that programming is merely the beginning of the journey. Generating new software, that's just the genesis. The real challenge, the actual discipline, is making sure that your code doesn't just completely crumble under its own weight as time passes, as user bases explode, and as underlying technologies inevitably shift. So we are basing this explainer on the foundational concepts from the incredible book Software Engineering at Google by Titus Winters, Tom Mantrek, and Hyrum. And what makes Google's perspective so uniquely valuable here is that they haven't just theorized about this. They've tested these concepts in a codebase of over 2 billion lines of code. 2 billion, maintained by tens of thousands of engineers over multiple decades. The authors really flip the traditional status quo on its head. They argue that to truly engineer software, we have to look at it through the lens of 3 critical dimensions: time, scale, and trade-offs. Here is our roadmap for the explainer today. We'll start by distinguishing programming from software engineering. Then we'll look at the passage of time and the trap of Hyrum's law. After that, we'll shift into how organizations scale and why early bug detection is so critical. Finally, we'll navigate engineering trade-offs and build the ultimate software engineering mindset. Let's get to it. Section 1: Programming versus software engineering. Notice the stark split between these two disciplines right here. On the left side, we have programming. It's short-term, it's usually an act of individual creation. Think about it, if you write a short-lived script and you use some highly obscure, undocumented API feature to make it run just a tiny bit faster, someone might look at that and call your code clever. And in the programming world, clever is a compliment. But look at the right side. Software engineering is long-term. It is inherently about team collaboration. If you write that exact same obscure, brittle code in a system that needs to be maintained by hundreds of other engineers for the next 10 years, well, clever suddenly becomes an accusation. It means your code is fragile. Software engineering isn't just the act of writing the code, it's the whole shebang. It's all the tools, the processes, the policies an organization uses to build and maintain that code over time. Just as cubes aren't squares, programming is definitely not software engineering. Section 2: Time, Change, and Sustainability. So the absolutely crucial point is right here on this timeline. Think for a second about the expected lifespan of your code. For a student script or a quick prototype, it might live for a few minutes or maybe a few days. But for a core back-end service at a major tech company, that could live for decades. Guys, that is a 100,000x gap in expected lifespans. If your code only lives for a few days, it's essentially immune to time. You don't have to worry about your operating system updating or your hardware changing or your dependencies being deprecated. But over a decade, literally every underlying foundation of your code is going to change. Software engineering means intentionally designing a system that can actually survive those changes. Notice how the necessity of upgrading your dependencies stays pretty flat for days, months, sometimes even years. It feels completely safe. But then, as we move into the years and decades, look at what happens. The curve spikes exponentially. Suddenly, an old library has a massive security flaw, or your legacy hardware is simply no longer supported. If your system is fundamentally incapable of reacting to a change in technology, you are placing a very high-risk bet. Sustainability really means you are capable of reacting to whatever valuable change comes along, whether for technical or business reasons, over the entire lifespan of your code. Section 3: The Trap of Hyrum's Law. If you take away just one concept from this explainer today, please make it Hyrum's law. It is basically the software equivalent of entropy. It states that with a sufficient number of users, every observable behavior of your system will eventually be depended on by someone. Honestly, it doesn't matter what your official documentation says. It doesn't matter what the API contract is. If your system does something visibly, a downstream user is going to build their software assuming it will always do that exact thing. Let's ground this with a classic real-world example, the hash ordering problem. So, by definition, a standard hash table does not guarantee internal ordering.
But let's say an engineer builds an API, and under the hood, it just so happens to return items in a specific, repeatable order, based on the current hash algorithm. Over time, programmers unknowingly build their own systems relying heavily on that exact output order. Fast forward a few years later, and you decide you want to do a simple compiler upgrade to make the hash algorithm faster. It's supposed to be a completely safe internal change. No big deal, right? But because of Hyrum's law, that invisible dependency has spread like wildfire. When you change the algorithm, the output order changes, and you instantly break thousands of user programs. These hidden dependencies turn completely innocuous upgrades into massive organizational bottlenecks.
Section 4, Scale and Shifting Left.
I want you to really challenge yourself with this question. Why do small team dynamics fail so spectacularly at scale? Look, when you have 5 engineers, you can just tap someone on the shoulder to ask how a module works. If the build takes an extra minute, whatever, it's no big deal. But if your organization grows by 10x or 100x, human interaction costs grow super linearly. If every single new developer adds manual overhead, you are on a deeply unsustainable path. It's a lot like the boiled frog metaphor. These slow, creeping inefficiencies just sneak up on a team. A 1-minute build delay multiplied by 5,000 engineers who are running 10 builds a day, that is a catastrophic loss of time and resources. True software engineering requires policies and automation that scales sublinearly with human input.
And speaking of scale, take a look at how the cost of a defect increases exponentially from development all the way to production. If you catch a bug while you're literally typing the code, it costs almost nothing to fix. If you catch it in testing, okay, it costs a little bit of compute time. But if a bug makes it all the way to production, now it requires incident response, massive rollbacks, customer support, and huge organizational coordination. This proves exactly why we absolutely must practice what is known as shifting left, which just means moving the detection of problems as early into the developer workflow as possible.
Let's walk through this lifecycle step by step so you can really see how this compounding works. At the concept and design phases, a flaw is literally just a conversation to fix. No code even written yet. In development, your IDE or compiler catches it instantly. But once you hit commit, it enters the continuous integration pipeline. Now it breaks the build, which blocks other engineers. If it slips all the way into production, you've got a live incident on your hands. In software engineering at scale, a massive part of the job is building the automated testing, the static analysis, and the code review systems that push quality control to the very left of this timeline. That is how you protect the larger organization from cascading failures.
Section 5, Navigating Engineering Trade-offs.
You know, everything in engineering is a push and pull trade-off. Do we prioritize speed so we can ship a feature immediately? Or do we prioritize safety by shifting left and writing extensive tests? Do we use a hard-coded quick path for simplicity? Or do we put in the work to design for future infrastructure flexibility? In a small weekend programming project, saying, because I said so or because it's faster, might fly. But in engineering at scale, that is never acceptable. Every single choice must evaluate explicit data, compute costs, and human maintenance costs over time. We aren't looking for magical, perfect answers here. We are looking for the most sustainable trade-off for our specific context.
Section 6, The Software Engineering Mindset. 100,000. Remember that massive multiplier we talked about earlier regarding a software's expected lifespan? To survive a multiplier like that, you have to adopt a true software engineering mindset. You need to start thinking of your codebase not as a static, dead document, but as a living city. And what does a city need? It needs infrastructure that can handle a booming population. It needs roads that can be upgraded without completely shutting down daily commerce. It needs rules that actually scale. The true engineering mindset requires automating your work, making database decisions rather than ego-driven ones, and architecting from day one for the absolute certainty of change.
I want to leave you all with this final provocative takeaway. Good programmers solve today's problem. Good software engineers build systems that can survive tomorrow's change. So the next time you sit down at your keyboard to write some code, ask yourself, are you just solving the immediate ticket right in front of you? Or are you engineering a resilient system that a developer you will never even meet, using hardware that hasn't even been invented yet, can safely maintain a decade from now? Thank you so much for joining me on this explainer. And keep